Okay, let us begin. Let's solve a differential equation. Let's solve dy dx equal x. Okay? This is a differential equation. It's called that because it has a derivative. Hey! Brandon, how you doing?
I've been better.
Oh, really?
Yeah.
Shoot. All right, we don't have to go into it, but I hope it gets better. Maybe my lecture will bring you up there. No, huh? Okay. A differential equation, because it has a derivative in it. Okay? And our job here is to find that function or set of functions that makes this equation true. We want to find that function or functions such that dy dx is equal to x. Can someone give me a solution to this differential equation? A function y is a function of x that makes that equation true.
X squared over 2 plus c.
Okay, well, let's start with x squared over 2. Okay, x squared over 2 is a solution to that differential equation. That is one solution. Let's graph this one solution. And we know it's a solution because when you take its derivative, you indeed get x back again. X squared over 2 would be a parabola that looks something like this, say. And what's true about this parabola is everywhere on this parabola, the slope of the tangent line, okay, the slope of the tangent line is equal to whatever the x coordinate is. So if this were at 2, say, and on the graph I'm at the point 2, 2, the slope of this tangent line at that point would be equal to x2. Okay? Slope of the tangent line, 2x over 2 would be x, which is equal to 2. That is a solution to this differential equation. But there are others, okay, which he implied by saying x squared over 2 plus a constant. Another solution would be y equals x squared over 2 plus 1. Adding 1 to that function does what to the graph? Shifts it up 1. Good. Nice. Where do we get this graph? Okay. Something like that anyways. And let's see what happens at 2. Now we're at the point 2, 3. What's the slope of the tangent line at this point? Well, if you take the derivative of this, we get x, our solution. When x is 2, we get the slope of 2 again. Okay? If I were to take x squared over 2 minus 1, that would be this graph. Take the same point, find the slope of the tangent line, its slope would also be 2. Okay? This is a family of functions, each of which solves that differential equation. And what he did, he generalized it to be y equals x squared over 2 plus a constant. Okay? Now, sometimes we're given a specific point through which the graph must pass. In other words, if we're given this solve, we may be given a point. Let's say it has to pass through the point 1, 3. This is called an initial condition. If at any time I say something that makes no sense, okay, you know what to do, right? You ask it, all right? No, just ask, all right? Just ask. Make sure you ask. All right, that's an initial condition. So we know the solution to this differential equation is y equals x squared over 2 plus a constant. Because it has this initial condition, this will enable us to solve for the constant c. X is 1, y is 3. Yes, go ahead.
Y equals x squared over 2 is given, or
Yes, this will have to be given.
no, that
See-
equation, y equals x squared over 2. That's given.
That's not given, no,
That's
no.
like always same?
If you're going to solve this differential equation, dy dx equals x,
Yeah.
the solution is x squared over 2 plus some constant,
Always, right?
always, for that differential equation. And that constant will raise up the graph or lower the graph. We can solve for the constant if we're given an additional point, okay, that initial condition. This will enable us to solve for c. So c is equal to 5/2. The solution to this differential equation, given this initial condition, is y equals x squared over 2 plus 5/2. Okay? It's that one solution, okay, of this family that passes through that point 1, 3. Okay? How we doing? Good deal. Now, differential equations, I'll tell you. If you're a double E, electrical engineering major, after you take Calc 1, Calc 2, and usually after you take Calc 3, what do? You take a whole semester of differential equations. Okay, where you learn different techniques solving differential equations. And differential equations have huge amount of application. I'll give you one example of an application of differential equations. In the early 1800s, you had Gauss, okay, Carl Friedrich Gauss, working on imaginary numbers, square roots of negative numbers. It was something he was just playing around with, right? And did some properties, proved some theorems, did a bunch of work, but then said, forget it. This is never going to be used to solve any problem in nature. And mathematicians at the time were they wanted their mathematics to solve problems, real world problems, okay? They weren't really after mathematics for its own sake, for the most part. So he just put the stuff away, and he said, forget it, I'm going to go on and do something more practical. Okay? 60 years later, the end of the 1800s, you have people like Marconi, Tesla, working on wireless transmission, okay? How to send a radio wave and embed in this radio wave information. It's still a mystery to me how to, but anyhow, how do you embed information on this radio wave, send it to someone so they can receive it and extract the information? It's an unbelievable thing. The mathematics is very complicated. It led to a system of differential equations. Marconi could not solve this this system. Somebody said to him, listen, that looks like what Gauss was working on 60 years ago. These imaginary numbers, these complex numbers, looks like it has the same kind of properties. So we went back and researched it, and sure enough, the work of Gauss provided the solution to these systems of differential equations. You take the system of differential equations, you go to complex numbers, solve it with the complex numbers, and they come back to the real numbers again. If you take differential equations here or anywhere else, you end up doing complex numbers. You have to do these complex numbers to solve these equations. And that led to the solution of that wireless transmission, which led to Lewis's phone right there. Okay, that's what it led to. All right? Just to let you know. But there are lots of other applications of differential equations. Certainly circuits. Any kind of a circuit is finding the current in a circuit at any given time. If you got inductors and capacitors and things like that, those are differential equations. Chemical reactions are differential equations. Population growth problems are differential equations. So lots of differential equation problems. So here we go with ours. I'm not going to do much with that one, but there it is. Okay, so we're solving that differential equation by finding the function y, whose derivative is Carolina. How you doing?
Good.
Good. Is the parking a problem? Is the traffic a problem? You just say yes, and I'll say, wow, you poor thing.
Yes.
Yes? Oh, you poor thing. All right. Okay. We've just started talking about, I know, we really, been talking for 26 minutes. I don't think I've said a heck of a lot. 26 minutes, yeah. But I haven't said much. Here's what I've said. You can have the notes, after. Okay. Okay. So we solved this differential equation. And how did we solve it, though? We looked at it, and we solved it by inspection, okay, is really what we did. We looked at it. We need a bit more formal approach to solving the differential equation in order to solve these things. We're going to need some additional notation is really what we need, okay? Okay. You okay? Okay. Here, well, I can give you this page, or you can just start at the next page, and I'll give you this at the end.
Yeah.
Yeah, okay, okay. That's better. Okay, let's go back to that same differential equation. Solve. dy dx equals x, okay? The procedure that we're going to use to solve these differential equations is the following. And this is what you would do day one in diff-EQs. If you take differential equations, day one, this is what you would do, okay? You would separate the variables. It's called separate the variables. Bring that dx on the other side. Now, you may protest and say, you know, dy dx, Burns, is not really a fraction. You're treating it like a fraction. It really is a limit. You know that dy dx is a limit as delta x goes to 0 of delta y over delta x. But the nice thing about this notation, this is due to Leibniz, okay, late 1600s notation, is that these things act like derivatives, okay, like fractions, all right? And we're taking advantage of that. I'm going to separate the variables, bring the dx over with x, and then I need a mechanism, a means to get to y. Think of this as taking the derivative of y. We need something that will get us back to y, the original. And guess what? That's an inverse function. That's what inverse functions do. They undo what functions do. If you start with y and take its derivative, and you want to get back to y, you take its antiderivative. Okay? And that's what we're going to do. And the symbol for that is this symbol right here. Okay? This is called, at this point, it's called an antiderivative. It's later going to be called an integral. Okay? We're going to take this antiderivative of both sides. Think of it as the inverse operation to taking a derivative. Okay? What happens here when I do this, I end up with y back again, the function we're looking for. Okay? What about this antiderivative of x dx, this integral of x dx? That's the function or functions whose derivative is x. He's already given us the answer. That's x squared over 2 plus c. How do we know that's true? Take the derivative. What's the derivative of x squared over 2? It's x. What's the derivative of the constant? It's 0. The derivative of this is x, therefore this is a true statement. Okay? That's what this notation means. This together with the dx means find that set of functions, that family of functions whose derivative is x. It's the antiderivative. Okay? All right, how are we doing? All right, what about something like this? And again, if you have initial condition, you can solve for c. What do you think this would be? That antiderivative of x squared, that family of functions whose derivative is x squared. What would that be?
X cubed over 2.
Over 3. Yep. Okay. Plus a constant. This gives us a family of functions, all of whom have a derivative of x squared. Okay? Because that's what the notation means. How do you know it's true? Take the derivative. What's the derivative of x cubed? 3x squared. The 3's will cancel. You'll get x squared. What's the derivative of c? 0. That's the antiderivative or integral. Okay? How we doing? All right, we're going to generalize this, okay? And we're going to have a list of integration forms or antiderivative forms, all right? Because that's what we do. We make lists of things, you know? All right, so, oh, what about this one? What would that integral be?
X
Yeah, x
plus C.
plus c, yeah. All right. How do you know it is? Take the derivative. What's the derivative of x? 1. Okay? That's what's understood to be in here. I'll tell you what we're going to do tonight. We're going to develop a whole bunch of rules for taking antiderivatives. Okay? That's what we're going to do. Okay? It's going to be fun. All right. I can stay here. Let's generalize what I've been doing. Let's do x to the n. N is some constant. We want to integrate x to the n. We want to find that family of functions whose derivative is x to the n. What do you think?
X to the n plus 1 over n plus 1.
Plus c. Very nice. That's exactly right. Okay? At this moment in time, this is what you should know. We're going to generalize this a little bit more next class, but right now, this is what I want you to know. There's a restriction on n here, of course. Okay? And obviously can't be -1. I'm going to make that explicit by saying n is not -1. Okay? Okay? How are we doing? Nice. There's one rule we have. X to the n. Let's get some more. Let's take care of that case where the n is -1. The integral of 1 over x. Okay, this is the case where n is -1. We can't use the rule that we just developed. We have to do something else. We need to find the function whose derivative is 1 over x. What function has a derivative of 1 over x? Natural log. Out of way. Good job. This is something we looked at last time when we found the derivative of natural log absolute value of u. We said it was 1 over u du dx. That gives us this solution. Okay? Let's do the integral of sine x. What is it? Cosine? Will cosine work?
Cosine plus c.
Well, plus c. Does that work? Not quite.
So it would be negative cosine?
Yeah. You need the opposite or a negative cosine in order to have its derivative equal to sine. Okay? The integral of cosine? That would be sine x. How do you know that's true? Take the derivative of sine, it's cosine. Okay? Let's take the derivative, let's take the integral rather of secant squared. That's tangent. Let's take the integral of secant tan. Secant. Nice. Now, how are we doing? We doing okay? Carolina, how you doing? You doing okay with this? Okay. Sam, you doing okay?
Yep.
Okay, good. Minus, you doing all right?
Yep.
Jim? Good deal. Okay. Egg? What? Alrighty. All right, let's see what else we have. What about this one? What's the antiderivative or integral of 1 over the square root of 1 minus x squared?
Inverse sine.
Inverse sine. Oh, wait, Jim. Inverse sine. Arc sine. Okay. It's an arc sine form. The integral of 1 over 1 plus x squared,
Understand?
or tangent,
Inverse tangent.
inverse tangent, arctangent, okay? 1 over the absolute value of x, square root of x squared minus 1. What is it?
Secant?
Yes, inverse secant. Okay. Let's see. I think that's it. I think that's all we need to know to begin with anyways. Is that it? You think of another? Go ahead.
Would there be cases that you have this and you have sine over cosine?
Oh yeah, we're going to develop more. This is a start. Okay. I
You
should
can't
put.
put a negative in, right?
What's that?
You can't put a negative in.
Yeah, we're going to have some properties.
Oh.
And one property will be any constant can take out front. We're going to do that next. And the integral of the sum is the sum of the integral, same with the difference. So we need some properties as well. Okay, we're going to need to do that. I just want to make sure this is our fundamental list, and we're all set here. I think this is it. We started with the x to the n on the other page. I'm just going to put that down the bottom so they're all on one page here. Okay, so we start with 3, 6. We have 9 of these to begin with. We're going to end up with about 16 or so integration forms that we need. We've already got 9. We've already got more than half, for Pete's sake. So it's not too bad. All right, this is not too bad. Okay, one thing I do want to mention, if you have okay, well, let's take care of some of the properties of this. One property is if we have the integral of f of x plus or minus g of x, it would make sense that the integral of a sum or difference is the sum or difference of the integrals. Why? Because we check it by taking the derivative, and the derivative of a sum or difference is the sum or difference of the derivatives. So, okay. It's a fundamental property. Another property of integrals, antiderivatives, is a constant times a function of x is equal to a constant times the integral of the function. Why would that be the case? Because when you take the derivative of a constant times a function, it's the constant times the derivative of the function. Okay? Okay, now you have quotient rules and product rules and derivatives. You don't have the same thing with the integrals. We'll have something later on called integration by parts for a product rule, but for a quotient rule, we never really have a quotient rule for integrals, okay? But we'll have integration by parts later on, all right? Okay, so given this is our starting point right here. So you should be able to do things like this. Find the integral of 3x squared minus 2x plus 5 dx. Go ahead. You guys do it. Okay.
X cubed minus x squared plus 5x.
Wow. Plus C, yeah. Good. Not to be picky or anything, but yeah. Okay. All right, how are we doing? Let's, we'll give everybody a minute or so here to make sure we're okay. Okay. How are we doing on this? Okay. So, this is what she did. She integrated each one of these terms. The first, here, let's write it out. And the first one, we can take the 3 out front, take the constant out front. We can take this constant out front, take this constant out front. The integral of x squared, that's our x to the n form here. That's x cubed over 3. The 3's will cancel. The integral of x, that's x to the first power. That's x squared over 2. The 2's will cancel. The integral of dx, we said before, was just plain x. You could think of this as x to the 0 power inside here, 1, and x to the first over 1, and apply this x to the n form. You get x plus c. Okay? Anybody else set on that? Wow, pretty cool. All right, good. Let me give you another one. Let's do the integral of, I don't know, sine x plus cosine x. Why don't you do that one? We're limited in what we can do because what we have to do next class is generalize these so we can get more interesting ones. But we have to start somewhere, right? Simple. That's all we can do. It's the kind of thing you're going to have in this homework. This is the 5.1 homework. Okay? It's the kind of thing you're going to have. Okay, what do you get here?
Negative cosine plus n
Very nice.
plus c.
Good deal. Okay, nice. Any questions on that? All right, well, I'll tell you what. Let's do an application. Let's go for an application here. We have rather limited integration powers, but we can still apply it to something. Okay. Here's the problem. Let's solve this problem. Okay? Let's suppose that if we go to the top of this building and toss something up at a certain initial velocity, it's going to go up some and then head down. Okay? It's going to head down. And let's suppose what we want to do is develop a formula to find out its position at any time t. Free fall formula. So that if we drop it with a 0 initial velocity, we can do it that way, we can toss it down, we can find its position at any time t. Okay? So here's what we know. Once you toss this, once you let it go, there's one force that's acting on this object. And what is that force?
Gravity.
That's gravity. So here's what we're starting with. Our acceleration is a negative g. Okay? That's what we're starting with. Here's what else we know. We know that at t equals 0, our velocity is v sub naught, our initial velocity. Okay? Whatever that is. If we drop it, initial velocity is 0. If we toss it up, okay, it's whatever that initial velocity is, positive. If we throw it down, that initial velocity will be negative. Okay? What else do we know? At t equals 0, its position is equal to s sub naught, whatever that initial position is. If we're at the top of this building, s sub naught would be, I don't know, 70 feet, something, 80, something like that. Who knows? I mean, somebody knows, I'm sure. Okay, so given this, can we derive a formula for position at any time t? And the answer is yes, as long as we know that acceleration here is how fast the velocity is changing. Okay? Acceleration is dv dt. It's how fast your velocity is changing. It's the rate of change of velocity. And what do we know? We know that that's equal to a negative g. If it's in feet per second, be a negative 32 feet per second. If we're in meters per second, we got a negative 9.8 meters per second. We have a differential equation to solve here. Let's solve it. Okay. Let's put the dt on the other side. Let's separate the variables. Okay. let's integrate each side. Okay. Now, what's the antiderivative or integral of dv? V. Nice. Actually, it's v plus a constant over here, but you got a constant here, you got a constant over there. We'll take the two constants, put them on one side, consolidate the constants. So we don't have to write the two constants, okay? Just the one constant on the right will be good enough. Now, g is a constant, okay? We can take that out front. What's the integral of dt? T. We can solve for this constant of integration by using one of our initial conditions. Namely, if t is equal to 0, v is v sub naught. So, at t equals 0, okay, here's what we have. Our velocity, v, is v sub naught. That's equal to a negative g times 0, okay, plus c. And this tells us that c is equal to v sub naught. Yes, Sam?
Why wouldn't you, after you do the dv integral and get v, why wouldn't there be a plus c after that?
Because, well, there is. But there is also a plus c after this one. And if I take this plus c and bring it over to the other side, I'll have one c minus another c. And you know what one c minus another c is? It's a c. It's a constant. So I just consolidate it into one.
Okay.
Okay? And that 1 is v sub naught. Okay? So here's what we have. V, our velocity at any time t, is equal to negative gt plus v sub naught. Okay? And by the way, I should mention that you may run across this notation as a function of time. Okay? V of t, velocity in terms of time. Either way. I'm not sure which way your website may do it this way, actually. Anyhow. Okay, that gives us the velocity at any time t. Okay. What we really wanted was the position at any time t. Well, let's see. How can we get there? What's the velocity equal to? How do you find velocity from position? What's the velocity? What is it?
Negative 32.
That would be the acceleration. How do you get, what is velocity? How do you find velocity? What is that?
The derivative?
Thank you. Thank you, Willis. I wasn't saying that really well. You saved me. You bailed me out, Willis. Thank you. Okay. The velocity is the derivative of position. It's how fast the position is changing. Okay. So ds dt is equal to a negative gt plus v sub. It's another differential equation. Okay. Separate the variables. Put the dt on the other side. Okay. Integrate. Take the antiderivative of each side. Okay. What's the integral of ds? S. That's our position at any time t. What's the integral of a negative gt, given that g is a constant?
Negative GT.
Yeah, that's what I'm asking you. The integral of negative gt.
Is it positive GT?
What is it?
Positive GT?
No.
Negative GT squared over 2.
Yes. Okay. Negative gt squared over 2. T is the variable here. We're integrating t to the first power, in which case you would add 1 to the exponent, t squared, and divide by 2. Okay? That's that x to the n form that we have. So you get negative g t squared over 2. Okay? Plus the integral of v sub naught t. V sub naught is a constant. Okay? What's the integral of v sub naught dt? Well, we're in T's now, we're not in X.
V sub O X.
BT?
Okay, what is it?
BT?
Well, put yours, but she said sub O, but that labels you an amateur. You know when you say sub O, you gotta say sub naught, okay? You can't say sub O. All right, sub naught is what you gotta say. All right, V sub naught T. Okay, you put you two together and you got it. Okay. All right, so V sub naught T plus a constant. Well, we're going to solve for the constant. Let's solve for the constant. Let's see what we have here. What do we know? We know that at t equals 0, S is S sub naught. Our position is our initial position. Okay? Therefore, S sub naught is equal to, let t equal 0, we get 0 here. We get 0 here. Let's see. That tells us that C is equal to S sub naught. That gives us the equation we're looking for. S, position at any time t, is equal to a negative gt squared over 2 plus V sub naught t plus S sub naught. Okay? Now, I got to tell you, this kind of operation, this kind of problem solving, we solved right here on a piece of paper. This was revolutionary in the 1600s because up until then, pretty much, laws of physics, laws of nature were discovered empirically, data. What people did, they looked at the moon, they wrote down the position of the moon at different times for years and years, and what they did, they tried to come up with a formula that would predict the position of the moon based on all this data. It was all empirically driven. But what happened was, no matter what kind of formula they came up with, they couldn't get one to match the position of the moon exactly. It was called perturbations of the lunar orbit. And it was one of the problems that Isaac Newton set out to solve. This problem of perturbations of the lunar orbit, when they couldn't get it exactly right, which led to gravitational attraction, okay? Which led to calculus. And he developed the calculus, really, in order to solve these problems of planetary motion. He just sat down there and solved these problems. Of course, in London, everybody else was dying of the plague, and he was out in the cottage on the countryside, having a good life. But anyhow, never mind that. He solved these problems, okay? By just sitting there doing mathematics, and it was a revolutionary thing. And then in the 1700s, then science just exploding. I mean, we got electromagnetism, we got all kinds of laws, planetary motions, the solar system, because people could do science and do laws of nature just by sitting down and doing it, and just by thinking about it. And that eventually gives rise to Einstein at the end, who did just thought experiments, just would sit down and think, and just think, you know, what if I'm on a beam of light bouncing off the clock, and I'm looking back at the clock, sitting on this photon, this beam of light. What happens to the clock as I move away from the clock, sitting on my beam of light? What happens to the clock? Nothing happens to the clock. I'm on this beam of light that says it's 6:55, and then okay, I'm on this beam, and it's on 6:55 exactly, and I'm looking back at the clock. The clock is not going to change. That beam of light is not going to change. And from that, he said, if I can travel the speed of light, that time will stand still. It doesn't move, because I'm on that one beam of light that's at exactly 6:55. And from that, you know, you get all these amazing mathematics about the laws of union. It's a little bit more complicated than that, but basically that's what he did. These thought experiments to develop these rules. Just amazing stuff. Oh gosh, it's good stuff. All right, let's do a problem on this. Let us do this problem. Tell you what, let you guys do this problem. Let's go to the top of this building. let's say it's, I don't know, 70 feet up, okay? That's our initial position. Let's take a pretzel or something, and we'll toss it up in the air, okay? And we'll give it an initial velocity. I don't know. How fast can you toss a pretzel up in the air? I have no idea. I don't Let's go with
15, 20 miles an hour. You
all
know,
right.
you get
Well, in feet per second. Let's go with 20 feet per second. Toss it up in the air, 20 feet per second. What kind of things can we do just by knowing? And we know gravity, of course, is negative 32 feet per second, okay? The negative is already built into the formula, by the way. All right, so we have that. Here are the kinds of things I want you to be able to do. First, how high does the pretzel go? What's its max height? How high does it go? How long is it in the air? What, you already got it? Wait, we're going to do this. Lois, take it easy. How long in the air? What's its velocity when it hits the ground? Now, obviously what we're going to do is neglect air resistance, okay? We're doing this thing in a vacuum, okay? Air resistance will play a huge role in this particular problem. Go ahead, you guys do it. We have three formulas that you have to use: an acceleration, we have a velocity formula, and we have a position formula. Given those three formulas, we ought to be able to solve these three questions. I got all those integration formulas. Did you get them all? Okay, well, constant, zero, sum or difference, x and sine, cosine, tangent, secant. I didn't do cotangent, cosecant. I probably should mention that. I think I will. There's a trick to them. I wouldn't give you those on a test, but I should mention those. Mohair. The other class, you're going to have to explain it to me, okay? I can't figure that out. Okay? Good.
Did you give us the position function?
Yeah, we just arrived at it. Negative 1 half gt squared plus, did we do it? Yeah, negative 1 half gt squared v sub naught t plus s sub naught.
Oh, negative 1/2, okay.
Yeah. Do you have it? Now, my plan is to record all the lectures, so if you do miss a class, hopefully I'll have it on a recording at least, so you can have that. Yes?
Are you gonna post it on like Blackboard?
I have my Count 3 lectures, most of them on YouTube. My plan is to do the same with these.
What's your camera name?
If you do a search on YouTube on Calculus STCC Burns, you'll find it. That's my Count 3 stuff. They take a while to get on. There's millions of hits, I think, so it's pretty.
Pretty premier YouTube content.
Premiere, yeah, that's it. Try to negotiate a big contract, big deal, get some money. Actually, 8 hits, I think it's the best. But anyhow. But anyhow, that's my plan. Okay, that's my plan. Now, Blackboard. I was told there'd be a problem with Blackboard because of the size of these videos. These videos get huge. I mean, I think it's recording now. So I think there's a size restriction on Blackboard. So I had to go to YouTube. And they're on there. It just requires effort on my part to organize it and to get them on there. And if I'm going to do this and somebody comes along and wants to play chess, I'm going to go play chess. You know what I mean? So I'm just saying, or if there's a barred owl at Arcadia in East Hampton, I'll probably take my camera and go there rather than do the YouTube. You know? So anyhow.
Did you say a barred owl?
There's a barred owl at, barred owl. Pretty common, barred owl at Arcadia. Matter of fact, we saw a barred owl this weekend at Fanny Stebbins in Long Meadow. There's a barred owl there. There's a place at Fanny Stebbins Nature Preserve along the Connecticut in Long Meadow. A really nice place. It's a nature preserve is what it is. And there's a barred owl in one area.
Sorry, what did you call the place in Long Meadow?
Fanny Stebbins. Fanny Stebbins. You do a search on that. It's along Route 5 in Long Meadow. Borders Connecticut River and Route 5. Yeah, there's a barred owl there. My son took a picture of a barred owl at Fanny Stebbins. The barred owl is kind of interesting because its defense is just to stay still. Okay, so you can like walk up to a barred owl and get like this close to it, and it'll just stare at you, but it won't move, thinking that you don't see it or so. I guess that's thinking. So he's got a picture of one. It's really cool. It's really neat. But anyhow. So there is a barred owl at Arcadia that's out in the open. I may go to see. What's that?
I just looked it up. It looks cool.
The barred owl? Yeah. Barred owls are pretty common here. Owls have two color, some have orange eyes and some have black eyes. The barred owl has black eyes. It's a cool owl. Any owl is cool. Owls are just cool. They're cool creatures. Okay, how are we doing? How high does the pretzel go? Wait, we should come right. We'll come wait for him. He's got the pretzels. Maybe he's trying it out. I don't know. Somebody one more time? Let me ask that. No, huh? Oh, fine. All right. How high does the pretzel go? Somebody have a height? Ooh, given the lack of response here, I don't have many confident people, do I, on this? Anybody? What's that?
I think that part wrong, but the time to the maximum height is at 0.625 seconds.
0.625 seconds. That does not seem reasonable to me. Although, wait, I'm only throwing it at 20 feet per second, and it's going down at 32 feet per second per second. That could be. That could very well be. Yeah, because you throw it up at 20, it's coming down at 32. After 1 second, it's heading downward at 32 feet per second minus the 20. So, yeah, it could be. Anybody have a max height? Go ahead, go.
That velocity was feet over second, right? Feet over second.
Wait, say that again now?
The velocity was feet over second, right?
The velocity, initial velocity is 20 feet per second. Yeah.
And the first one, yes, is just 70 feet, right?
And the first one is 70 feet. Okay. All right. I don't know. You want me to do it? I have a feeling some of you have an answer, but are a little bit reluctant to be wrong. Okay. But this being wrong is, there's nothing wrong with that. I mean, actually, if you give an answer and it's wrong, after I get done laughing at you, it's not a big deal. You know? I would.
76.25 feet.
What do you think? I don't know what the answer is. You're saying 76? It doesn't seem right. It doesn't. It seems like it must go higher, but maybe not, because you're not throwing it up very hard. You know, with only 20 feet per second, that's feeble. Okay, so it's just going to go up. It's immediately start coming down. So that could be right. Anybody with a different answer? He's got 76 and a quarter. Anybody with a different answer? PP? No? You had that? Oh, wow.
20 feet?
Well, it's starting at 70 minus.
Oh.
Okay, so it's going to be greater than 70. It's going to go up something. Okay.
Maybe 90?
What's that?
90 feet per second?
90 feet as initial height? Could be. I don't know. We're going to do it out. We're going to do it out. And I just want to see if anybody else wants to get on record here. Carolina? No, we don't want to get on record? Fine. All right, let's try it. Well, what do we have for formulas here? We have S equals this is the formula we derive for S. We have our velocity formula, okay? And we have acceleration. Okay? All right, let's do the first question. How high does the pretzel go? Well, at max height, what's its velocity equal to? 0. It's equal to 0. Okay? So that's the way I'm going to do that. Okay? I'm going to find the time it takes to reach max height, to find the time it takes for the velocity to be 0. Okay? So let's take the velocity. And set it equal to 0. Okay? This will be the time it takes. Now, think about this a minute. We want to maximize the height. We want to maximize its position from the ground. How do you find a max min? How do you do max min problems? Well, you get an expression for the quantity to be maximized or minimized, and then you take its derivative, and what's the derivative of S? It's V, and set it equal to 0. That's how you find max min values, right? You take derivatives of the function and set them equal to 0. That gives you the critical values. So the derivative of position is velocity. I'm going to find the max height by setting the velocity equal to 0. The velocity, which is the derivative of position. All right, now, Carolina, talk to me.
How did you get the negative 32?
32, the negative is built into this as far as the acceleration due to gravity. We're in feet per second, and G in feet per second is a negative 32 feet per second per second. If we were in meters per second, it would be a 9.8, okay? All right, so let's set this equal to 0, and we'll get negative 32t is a negative 20. T is equal to 20 over 32 for just exactly what he said. Okay. Okay. Dylan, where's Dylan?
Bonnie,
What's that?
Bonnie, that.
Okay, okay, okay. Okay, good. All right, 5/8, 0.625. I think that's what he said, right? So that's pretty quick. We're throwing it up in such a feeble way that's just going to go up there a little tiny bit and then head down. How high does it get? Well, let's see. What's its position at 5/8? That's how high it will get. So we'll take this value, substitute it in for the position. S is equal to a negative 32 t squared. Ugh. All right, I'm going to need calculator help here. Plus v sub naught t plus s sub naught. Okay. So I'm going to need this rounded off, say the nearest tenth. Can someone crank this out for me? Oh, good.
I got 70.
You have what?
I got 70. At first I thought it didn't make sense.
You got 70?
Wait, it's
76.2.
Oh.
That sounds better. That sounds better. Because it must go somewhere. I mean, it goes up a little bit. Okay? All right. Are you guys? Okay. You guys all right? Okay. Okay, you're not going to fight or anything. You guys are all right, right?
No, I was just.
All right, then. Okay, no problem. All right, no problem. Where'd you get, Mohit?
76.25.
76 point, let's go with 3 feet. We'll round the nearest tenth. Okay? Okay. Everybody else set on that? Is that reasonable here? You know, I'm going to tell you that last time we went over derivatives from Calc 1, there are other things I'm going to assume that you know from Calc 1. Like, for example, to solve a max-min problem, okay, take a derivative, set it equal to 0, okay? Occasionally, you're going to have these problems in homework. Test questions probably won't do something like that, but there are certain things from Calc 1 I would expect you to know. The significance of the first derivative when it comes to curve sketching, okay? Increasing, decreasing function. A second derivative, meaning concave up or concave down. Those kinds of things I would expect you to know. If we ever needed them, I would go over them in class, but you should know those things, okay? That's what I'm saying. Okay. How long is this thing in the air? Whoa. How are we going to figure that out? How long is it going to be in the air? What are we going to do to find that problem?
Set S to 0.
Set S equal to 0. That's exactly right. Okay? So, question 1. Dylan, you were totally correct. Not that that surprises you at all. The time is 0.625 seconds. Gets to 76.3 feet. That's the max height. Now we're doing how long it is in the air, and we're going to find that one. This is number 1. Number 2, how long in the air we're going to set S equal to 0. So S is equal to a negative 16 t squared plus 20t plus 70. Well, what the heck is this? I need someone with a good calculator to crank out this solution to this differential equation, this quadratic here. 2.8 seconds? Good deal. Okay, so t is approximately 2.8 seconds. Okay, nice. That's how long it is in the air. What's the velocity when it hits the ground? We're going to take our 2.8 seconds and we're going to put it into our velocity formula to find the velocity when it hits the ground. The velocity is equal to negative 32 t.
What did you make S equal to for number 2?
0.
Wouldn't that be how long before it gets back to its original point?
No. The original point is 70 feet up, S sub naught. The ground is 0. You could do the problem that way, Brendan. You could do the problem that your starting point is 0, but almost always you want ground to be 0. It makes the problems easier to do. Okay. You could do it your way if you wanted to. No. Get the wrong answer. No, you would get the right answer. I'm sorry. Oh, you had a bad day too, and here I am making stupid jokes. I'm sorry. Okay. I'm sorry. All right. The velocity of negative 32t is 2.8. Initial velocity was 20. I don't know. What do we get here? What's our velocity when it hits the ground?
69.6 feet per second.
What is it?
69.6 feet per second.
Thank you. Okay. How we doing? Okay. Does that seem reasonable? We didn't have that many people getting it, though. All right, let's do one more. It's illegal. Well, I don't think you can do it now. It used to be you can go to the top of the Empire State Building and throw something off. I haven't been there in a long time, but I don't know if you can still. But it's illegal to do such a thing because whatever you throw, except for something like popcorn or something, if you threw a coin up there, you could kill somebody down below. So here's what I want you to do. Let's just figure this out. Let's suppose you're dropping something from the top of the Empire State Building, 1,000 feet up, okay? What's the velocity when it hits the ground? So, go ahead. Just want to see if we got more people getting this thing. I don't think we had that many last time.
How fast is it traveling?
Yeah, what's the velocity when it hits the ground?
Oh,
And again, we're
How tall is it?
1,000 feet. We're dropping
instead of coin.
a coin. What's that?
They busted it on Mythbusters.
They did what?
They put it on Mythbusters. And they won't. Like, you drop a coin off of the Empire State Building, it won't kill somebody.
You won't?
It won't.
They tested this out?
Yeah, like they figured out like the velocity, how fast it would go.
Yeah, there's a terminal velocity problem here with air resistance.
And
I don't want to get hit by that thing. And it won't kill somebody? What's the terminal velocity about? 100? I don't know.
But they made like a gelatin head, and they like
Oh, really?
they like shot a quarter at it, and it didn't even puncture it.
Well, that's if your head's made of gelatin. Your head made out of gelatin?
Well, but it didn't like go inside the person's head.
Oh, really?
Yeah.
Oh.
Which I thought it would, but
I thought it would too, but I know there is a terminal velocity, and it depends on the shape of the coin. I mean, certain coins would be slightly different terminal velocities because of the air resistance problem here. But that's interesting. So you're telling me it's legal now to toss coins off the Empire State
well, I don't know about that.
Building? Yeah, I don't-
Somebody
I
throw
don't
a
think
phone
so.
off of it, and then I'll kill someone. But
Yeah. All right, we're gonna toss a coin. We're gonna drop a coin off the top. We're gonna find out what its velocity is when it hits the ground. But again, we're neglecting air resistance here, which is a significant thing. Okay, because there is such a thing as terminal velocity, depending on the aerodynamics of the thing that's being tossed. It'll go so fast and not any faster. You got it, Dylan?
I'll keep my mouth shut this
What?
time. Other people didn't get it, so this guy will just stay quiet.
Oh, no, it was nothing to do with you. I don't, no, you were fine. You were fine.
What is it, section 1 here? This one?
This is 4. Oh, what book is this?
See, this is a 6th edition.
Yeah, that's not even,
After, right? Because we have-
well, it's we have the alternate version, 5th edition. This doesn't say early transcendentals either, but it has them here.
Right, and when it doesn't, but it's weird, like where like the first,
That's interesting.
immigration and then other transcendental functions.
Oh, my. Okay, other ones. Okay, so in the alternate book, this stuff, it comes first.
So they
Yeah.
still do the trig stuff before.
Well, I see that, yeah.
But I got it for $5, so.
$5? Is that it? Oh, that's cool. That's good good deal.
Yeah.
Oh, all the stuff is here.
Yeah, it's all there.
Well, let's see what the problems. Problems are,
Which ones are usually pretty consistent then after that more?
yeah, I don't know how many of these you have in your homework, so. So there's the bomb. Oh, they have quite a, oh, look at those. There's a lot of tossing, but I don't think you have many of those in the WebAssign stuff. Yeah, you guys can solve this.
Actually, that's one like its acceleration. If you look at downtown and choose a movie and you should get to throw a grenade out of a wall or something, you have to do that one class.
Really?
Times.
Wow. Wow. That's interesting. Huh. Wow. Pretty cool. Okay, how are we doing? All right, let's get some more people with the answer. What do we have for an answer?
Negative 233.
Negative 233. It is heading downward. It would be negative. Negative 233 feet per second. Anybody want to disagree with her? She said it with some. Yeah.
I'm not sure.
Okay, that's okay. You said it, and that's good. But you have formidable competition here with these guys. Okay, BP.
I got negative 250 there.
Yeah,
253. 253.
Yeah,
No.
252.8.
You forgot to add the 20 if you got 2.
Oh yeah, that's what it is, huh? Wait, 20. What's the 20? No, we just dropped it. There is no 20.
Yeah.
Maybe they're all wrong, and you're right.
D naught 0. So
What's that?
because it cancels out.
Oh, that was from the
She's
last
using
thing.
the last one. Yeah.
Oh. All right, no problem. No problem. Let's do it. Okay. So what do we know? S sub naught is equal to 1,000. We want to find the velocity when it hits the ground. Let's find the time it takes to hit the ground. Okay? The time it takes S to be equal to 0. So we want a negative 16t squared plus 0t. Okay, that's our initial velocity, plus 1,000 to be equal to 0. Okay, hitting the ground, that's 0. This is 0 here. We end up with t squared is equal to 1,000 over 16. So t is the square root of 1,000 over 16, which we could simplify significantly here. 1,000 over 16 is equal to, what is that equal to? 16 and a half?
62 and a half.
62 and a half. Wow, that same 625 thing. That's interesting.
But I need to take it under the.
Okay, that's a square root. You got to take the square root, right? Because it's not going to be in the air that long, that's for sure. So, and that's exact. This is exact. Okay, this is now an approximation. And what'd you get for a time here?
7.9, so it's almost 8.
7.9. Okay, good deal. Seconds. 8 seconds in the air. Hey, that's about right. Okay. Now, what's the velocity at that time? Take the velocity. Okay. Which is a negative 32t plus initial velocity of 0. Substitute in the 7.9. And we get our velocity of approximately, would you guys get 253 feet per second? Okay. How are we doing? Is that okay? Good deal. Okay. Here's what I want you to do. I want you to do 5.1 for homework. Okay? Get on WebAssign. Make sure you get on WebAssign and do 5.1. That's important homework. It's an introduction to the integrals. It's what we're going to be doing this whole semester. So I want you to be able to do those integrals, crank those integrals out, make sure you can do them. What we're going to do is generalize those integrals and introduce some more. Okay, we're going to almost double the list, and we're going to generalize them too. So we're going to be doing that next time. Yes, Louis.
Did you give our syllabus?
Syllabus is on WebAssign.
It's on website.
Yes.
So 16 is always constant, and then negative 16?
As long as you're using feet per second, yes. As long as you have a negative g over 2 kind of a thing, as long as you divide by 2, which you will do.
Yeah.
Anybody else?
Really? So,
So we just do the first one.
Oh, wow. A new student.
oh, really?
Are you in this class?
Yeah. 'cause I'm-
Oh, you just signed up today?
No, I was here Monday.
Oh, okay. What's your last name?
Dupree?
Levi.
Yes.
Okay.